There is a unique opportunity today. Natural gas is a cleaner fossil fuel than petroleum or coal, and with the vast amounts of natural gas being discovered in the US around the world, this could be an opportune time to transition from an oil-based to a natural gas-based economy. Natural gas is composed of the molecules methane, ethane, and propane. That is some of the least reactive molecules known in chemistry. It's because of this low reactivity that the current technologies utilize the high temperature processes that can be very complex and expensive. In fact, the capital cost of some of these plants can be in the billions of dollars. As a result of this, the chemicals and fuels generated from natural gas technologies today can't compete with products generated from petroleum. However, studies have shown that if natural gas processes could be developed that operate at lower temperatures and in one step, that the chemicals and fuels produced could be economically competitive with those produced from petroleum. Unfortunately, the chemistry to enable this technology doesn't exist today. This has been a long-standing challenge and has been considered one of the holy grails in chemistry. The current technology for natural gas conversion utilizes solids to facilitate the high temperature reactions. Interestingly, even though these materials have been around since the 19th century, we still can't engineer them sufficiently to allow reaction at lower temperatures with selectivity. Now, our approach has been to use molecules instead of solids. The key reason for this is that we can design molecules with almost full control given the well-established methods and synthetic tools we have today. Now, the molecule shown in this video is not the one we've utilized in the study, but it does show the essential features. The real key to the efficiency of our systems is shown here, where, as you can see, when the CH bond breaks, that the fragments, the carbon and hydrogen fragments, are bound to the molecules. That allows this reaction to proceed at low temperatures and for the reaction to be controlled. This is what leads to these very fast rates at high temperatures and the high selectivity of the reaction. We've been working on this challenge for many years. In earlier work, we were successful in developing molecules that allowed reactions with alkanes at low temperatures. Unfortunately, these systems were based on precious metals such as platinum, palladium, and gold that simply were impractical. Other key disadvantages with these early systems were that the reactions were unselective with the other alkanes in natural gas, and that these systems also utilized superacid media. Now, the new molecules we've discovered are actually non-precious metals, and they're based on simple, common, inexpensive so-called main group salts such as lead or thallium. The advantages of these materials are that they can react with the alkanes at temperatures below 200 degrees, and importantly, they lead directly to alcohol products with very high specificity. What's also exciting is that these materials have never been used in this way before, and this opens up a new class of molecules that can be considered, as well as new ways of thinking. We've been able to develop molecular models. We have a full understanding of these systems, and we expect that other simple, inexpensive main group elements, such as bismuth and iodine, as well as others, could be utilized for these conversions. Now, it's important to understand that the systems we report in this article are not ready for commercialization. However, because of the simplicity, the fast reactions, and the high selectivity, as well as our new insights, we're optimistic that with further research, that these could be utilized in practical applications. The potential for using natural gas to make our chemical building blocks and fuels is vast. As you can see, the current technologies utilize high temperature greater than 800 degrees and multiple steps to make these materials. If we could utilize lower temperatures, around 200-degree technology, that generates these products in one step, not only would we save billions in dollars, but we could also reduce the carbon footprint of these essential processes. Now, this has been known for a while, and it's been considered that implementing such technology could lead to a paradigm change in the petrochemical industry.